Next up, we got Brian Pailes, Principal Engineer with Vector Corrosion Services, and the topic's finding a 15-year follow-up on the use of surface anodes, deteriorated pier caps.
Thank you for having me here. I'd like to actually present. I'm really the co-author. Paul Parlarski of Minnesota DOT. He's the one who kind of put this together and issued it through, and he wasn't going to be able to make it, so he pressed me into service here to present on his behalf. So this is a joint work this is actually a project VCS did for MnDOT, did a report, and so I'll be presenting that. This is a project on a bridge in Jordan, Minnesota. So it's Bridge 9123. So Jordan there, southwest of Minneapolis. And you can see it's a little bridge over a railroad. So here's the bridge. So what this bridge is just a 5-span, 4-pier bridge over some railroad tracks in kind of, I guess, rural Minnesota. And what they did with this bridge is kind of unique. It was a part of a trial project. So this bridge was originally constructed in 1957. Between 97 and 2000, the substructure had an MBI of 6. And then from 2000 to 2005, that substructure dropped to a 5. And so then in 2005, they decided to do some restoration of the bridge. And so they did concrete repair work of the substructure. The unique thing of this was, this allowed MnDOT to kind of do a trial. And so what they did was on piers 1 and 2, they only did concrete repair work. But on piers 3 and 4, they did the concrete repair work, but on the bent caps, they decided to use a surface-applied cathodic protection system to kind of demo to see would this add extended service life to those pier caps. One important thing to note is that the concrete repairs were done using shotcrete. Just to kind of, forgive me, but because this is kind of Paul's presentation, I'm going to be kind of almost talking as MnDOT here from their perspective. So for this presentation, I'm kind of a MnDOT employee / presenter here for them. So, what MnDOT was trying to do was look at trialing a new CP product. You got to give real good credit to these DOTs, always trying to do new things. Giving some trial, looking at new things to see if they're going to be effective and they can implement it further. MnDOT is always looking for more cost-effective repair solutions, like everyone here in this room. They aim to be progressive and do trials for research purposes, for implementing new technology. However, there are challenges in that. And, as I move through this project, these challenges will kind of surface in kind of the conclusions, but there are often difficulties in knowledge transfer, especially, with something like this, there were no maintenance manual or understanding how the system works. So effectively, when we got involved in this project, they didn't really have much information about what the trial had done because there was these knowledge transfer issues over the last 15 years. So that's a difficulty when state DOTs are doing these long-term projects is, what is the documentation and monitoring of those systems in these trials? What steps are done required to maintain the system? And then also personnel changes, right? In 15 years, people change, people move jobs, new hires come in, and often knowledge transfer is often limited to immediate needs. Somebody coming in new, you're just going to kind of transfer what the immediate things are. You're going to forget about this trial you have out on Jordan, Minnesota, 10 years ago. So these are some of the difficulties that go into doing trials like these. So this is what the pier cap looks like now. So effectively in 2020 we came out to do a survey, and so this is so the picture on the left there is Pier 1, and picture on the right there is actually Pier 3. And you can see the pier cap on the right there has that gray coating on it. And so that is the cathodic protection anode just on the cap there under an expansion joint. And you can see, obviously, there's a lot of graffiti on the bridge. So the system is actually, that was used is called Galvacor. It's supplied by Cortec Corporation. So this is actually, Andrew was just presenting on a zinc metallized system, which is a melted zinc sprayed onto the surface. So this is a little bit different kind of cathodic protection system. This is a kind of spread on material. And I wouldn't use the word paint, but for lack of a better word, it's kind of a spread on material like that. And so it's a 3-component material. So it's like a cure resin, a metal-rich component, which is like a zinc or aluminum metal. That's a galvanic anode. and then an activator, something that when we do galvanic cathodic protection, we want the galvanic system to want to corrode, because that's what provides the protection to the structure. So this 3-part gets mixed together and then applied onto the surface of the structure, and then a urethane coating goes over it. So that, back in 2000, this was the material that was applied to that pier cap. Just a quick little background, how does galvanic cathodic protection work? So this is a sacrificial metal. So, Andrew was just talking about impressed current, where he has rectifiers, he's got a power source. This is a galvanic system where we take a sacrificial metal, we directly connect that to the steel we want to protect. That sacrificial metal sacrificially corrodes, gives up its electrons to protect the steel. So there is current flow through the direct metal path between the steel and the anode, and there's ionic current flow through the electrolyte, which would be, in this case, concrete. So there's this electrical current circuit that's occurring between the galvanic anode and the steel. And that's how the galvanic anode will protect the steel from corrosion. In 2020, MnDOT asked VCS to perform an evaluation of this system to understand its current status and its effectiveness over the last 15 years. Unfortunately, like I mentioned, the difficulties in this project were, other than routine bridge inspection on this structure, nobody knew how that system had done. No one had evaluated or maintained it. So really the goal was to determine if there were any benefits to this product at substantially decreasing reoccurring pier repair needs. So that was the goal. Okay, over the last 15 years, did it help limit concrete repairs for those 2 pier caps? The reason this kind of got brought to the forefront was because this bridge was due to be replaced. The bridge railings were very poor, and so effectively the bridge was deteriorating in other places that was so severe that it really didn't make sense for the DOT to invest in substructure repairs on the piers that don't have anything. And so it was just kind of decided that this bridge wasn't worth saving. It's better to just remove and replace it. So, kind of since they're about to remove the bridge, it gave a good opportunity for us to kind of study to see, are the pier caps on 3 and 4 any better than the pier caps on 1 and 2? This is what the system kind of looked like when we got there. So you can kind of see the bents in the background there. You can see bents 1, 2, and then 3 in the foreground here. You can see the gray materials, that galvanic anode. Obviously, over 15 years, we're starting to lose some of it in certain areas. Granted, this is a sacrificial system, right? So sacrificial systems are to deteriorate as they protect. There you can see the conduit running the various zones. So this was monitored. So the idea with this was there was some wiring for this system so that it could be monitored over the course of its life to see its performance. Unfortunately, that didn't actually happen, but it was set up and wired to do that. You could install this without monitoring, so effectively you could directly, what we would call a short, you could short this system directly to the steel and not have any external cabling or wiring, and let the system work as it's intended. But because of monitoring, you want to have, you effectively isolate the steel and anode and then go through a circuit. Again, here's some other photos. Here, again, we can see water staining coming down from the deck joint. So obviously, that's the source of the problem for these pier caps, is expansion joints, de-icing salts coming down. We see some corrosion of spall there, so that's not a great sign that, okay, we did have some corrosion in this pier. So how the system kind of works is that galvanic anode is spread on the surface of the concrete, but the current, this system has kind of distribution bars to help kind of even the current flow between the anode and the steel. And so you can see in the photo there those metal strips, and that's just, it's kind of a unique feature of this this product, is that it has these strips that are used to connect to the reinforcement to help kind of even the circuit resistance and distribute the current flow. Because as that galvanic anode starts to degrade, you're going to get higher resistance in areas. So that bar, we would call a distribution bar, was there to kind of help distribute that. But in some areas, we were seeing that failing after the 15 years here. So a monitor system, so obviously this isn't 15 years ago. This is Galvanic. It's a very basic monitoring. So effectively, they had the wiring to a simple little amp meter, a little analog amp meter. And you can see we've opened a box here on the structure. You've got the red wires for the anode and the green wires for the steel connection, and then effectively current flows between the anode and the steel. And so with that amp meter, you're supposed to be able to measure that. Now, it wouldn't be surprising that, over 15 years that amp meter doesn't work at all. It does read 0 at the situation. We did take our own meters and check everything. Unfortunately, it did also read 0, so there was no current flowing at the time, but I'll get into that here in a sec. You can kind of see, unfortunately, without a lack of maintenance over those 15 years, without a lack of somebody looking after this 15 years, there were some issues. Seeing here's a conduit, and we don't see, we see a T-junction there, and then, I don't know if there was an existing piece of conduit that came down to that connection, or they just had the wires exposed like that, but that's obviously not a good sign at this time. Some damage to the conduit, some damage to the wiring. And that was kind of uniform, so we kind of think that when they installed it, they didn't really have really good conduit routing, so they just had these T-junctions and then ran the wire externally. 15 years ago, that's really not good practice these days. If someone's installing CP these days, they would have conduit runs all the way to the concrete so that all those wires are encased and protected. Because if you have wires exposed like that, they can get damaged, and that'll affect the performance of your system. So obviously, I showed that amp meter. We got our actual meters out, and unfortunately, when we came to site 15 years after installation, there was no current flowing between any of the anodes on Pier 3 or 4. Inspection of the system identified that really most of the anode and structure connections had failed because they just weren't properly connected and durable for a 15-year service life. So some issues on the initial installation that affected durability. Those things can be kind of picked up if you're monitoring and maintenance of a system, but unfortunately that wasn't done in this situation here. Some of the difficulties in this was an early application for this galvanic system. It was one of the early trials for it, so they didn't quite have all the quote-unquote bugs worked out. They only put 10 mil thickness for this coating back in the original bid documents, but actually specifications for this product nowadays actually call out for 24 mils. So we kind of think that in the early days, they went too low in a trial and then realized that they needed a little bit more thickness for durability and galvanic anode. Thickness of this on this 2 piers was lower than probably what should have been, so that probably hurt some of the durability. One thing too, I mentioned shotcrete. Shotcrete is really highly resistive because it has a lot of silica fume in it. So whenever you're doing cathodic protection and there's shotcrete repairs, that kind of, to a CP person, brings a little bit of alarm, because if we got to push current through the concrete. So if we have really high resistive concrete, that'll affect the performance and current flow from that anode. Because of the high resistivity of that material. Typically, if you're going to use shotcrete, then we have to do some pre-packing of anodes or some low resistive paths to help guide current through the shotcrete, or use another type of material. So probably 15 years ago, they weren't really, the people doing the concrete repair work weren't coordinating with this one trial on these 2 piers, right? They went out, did the shotcrete, did the repair work, and left, and then somebody else came in to do this trial. And so there was a lack of coordination on the repair material. And so that kind of put the system at a little bit of a disadvantage there. And so, you don't want to kind of, we're not seeing current flowing from this anode, but, not everything is, I don't want to say that the anode didn't work, right? There were some issues that really didn't set it up for that 15-year service life. We also did, delamination survey, right? That's kind of the big key here is, did the system work or not? What are the current delaminations in 2020, when we were out there? Was there more delamination on piers 1 and 2 versus 3 or 4, or was it relatively the same? And so here, this is just an example of the delamination survey from the 3 faces of Pier 1 cap. So you've got the 2 vertical faces in the underside, and the hatching is where the delaminations are on that one. And then if we go to Pier 4, which had the CP, you can see there's pretty significant delamination, effectively the same amount of surface area, unfortunately. So if I take just the south face for the Pier 1 and Pier 4, effectively there's really no difference between the two. So that's an unfortunate sign that really it didn't really provide much benefit. We still have a lot of concrete repair work there. And kind of just looking at overall, we kind of see that Piers 2 and 3 were very similar, and Piers 1 and 4 were very similar. I don't know if there's some geometry situation on this bridge that made the Piers 1 and 4 very similar to 3 and 2. Similar, but they had expansion joints over them, and so de-icing salt's coming down. So unfortunately, based on kind of just the sounding inspection, this system didn't really provide a lot of benefit. But I want to make sure that the caveat is there that there were some things that really it wasn't properly maintained. There were some issues with applying shotcrete, so current flow problems. So was this really set up the best way at the beginning? I would contend probably not. So we also did some corrosion potential measurements to look at corrosion activity on the elements. And so you can kind of see, so corrosion potential measurements are for ASTM C876. And so what we're doing there is we've got a reference electrode, and we're measuring the potential of that reference electrode against the steel reinforcement. And the potential will tell us the potential risk for corrosion activity of that steel reinforcement. And so you see here this gentleman in the bottom right corner there, he's got that reference electrode, and he's looking where the active corrosion is beyond what the concrete is delaminated. So the white hatching there, you can see we've already gone and done a delamination survey. And by the way, this photo is not from that structure. It's a different structure, but just for example purposes. So, obviously you have where the concrete is delaminated, but you also want to know where the active corrosion is beyond the delaminations. And so, kind of going out, and this is actually happens to be, I believe, Pier 1, but kind of indicative of what we were seeing on the structure as a whole. So we went and corrosion potential surveyed all of the substructure. And this structure was very actively corroding. Those warm colors are high probability of active corrosion. So most everywhere on that pier is actively corroding on that pier cap on Pier 1. And the columns were very much the same. So this bridge was very severely deteriorated, had a lot of chloride exposure over the years, really hasn't been maintained since 15 years ago. So that, that's again a driver for why this bridge had to be replaced. And so, again, kind of puts it at a disadvantage. In kind of conclusion on that evaluation of the CP system, unfortunately, it didn't really provide an extension in this situation. This was something that we'd hoped that, cathodic protection really does work. It provides protection, but the system connections weren't really durable and had early failures. So unfortunately, some things that happened during the initial installation didn't really set it up to last the 15 years. The conduit runs, the wiring that was exposed, those weren't really durable, didn't last the 15 years. And then the lack of inspection and maintenance, right? Anytime you have kind of a system like this, it's important to go out and inspect it. I mean, not super regularly, but fairly often, just to make sure that things are working properly. Those connections can easily be fixed. Those aren't like detrimental. You have a structure connection that goes bad, you can get that back in relatively simply. So, had been some inspection and maintenance over the course of that life, could have gotten that system back up and running and to provide some protection. And then also some issues at the beginning with probably a little bit thinner application than was really recommended, and the shotcrete, which limited the galvanic protection flow. So those are some things that allowed it not really to perform as well as it should have. What did we learn from this? I think, Paul really learned from this is better tracking and monitoring these trials, right? If you're going to spend the money to try to trial something and potentially use a new product for mitigating damage, it's important to track and monitor these, kind of understanding the monitoring and maintenance requirements of a system. DOTs don't have a lot of experience. Some DOTs don't have a lot of experience in cathodic protection. So when you get a system like that, understanding what the monitoring and maintenance requirements of that system are. Some systems have a lot of monitoring and maintenance requirements. Some have minor ones. But really understanding those requirements is really critical to make sure that system will be durable. And like I said, external components, when you're monitoring, are a potential weak point and need to be inspected and repaired as they deteriorate. Unfortunately, this application didn't lengthen the service life of the bridge. Other elements actually controlled the service life of this bridge anyway. So it wasn't really, so even if the system had worked on the pier caps, they still would have had to replace this bridge because railings and other things were deteriorating faster. And so really the takeaway there is right-sizing the service life investment amongst all other elements, right? If you spend all this money on these pier caps, but then the bridge railings cause the bridge to get replaced, well, even if the CP system had worked, that really wasn't that smart of an investment. So not only understanding this application, but how it affects as a global application on that bridge is a really important takeaway from this project is even if that system had worked on those caps, the bridge still would have been replaced. So, granted this was a trial, but just thinking about this in a more real application, had they done that system all over the substructure, even if it had worked, they still would have had to replace the bridge because of the issues up top. So selecting the right system to kind of match the service life of the bridge as a whole is really critical to make sure you're using your money effectively and preserving a structure in the right way. With that, I hope I talked on behalf of Paul in a fair way, and that if there's any questions, I'm happy to answer anything that you have. Yeah, I didn't do the Minnesota accent. I should have really practiced that.
You sounded like Paul too, Brian. That's good. Well, I have a quick question. You mentioned that nowadays this particular anode uses 24 mil thickness. Is this anode even available today?
Well, the latest product information that I could find, I don't even think it's available anymore, actually.
Okay, so this is no longer available. Okay.
Yeah. Or at least not this generation. I think they have a different series of it, but yeah.
Not from this manufacturer.
No, yeah. So, but
They want to wait.
when they were in full-scale production, they recommended 24.
Thank you, Brian.
Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.